All right, this is optimization, and I've got 4 more examples to go through. These are the last 4 from our notes, so let's just get started. So it says a rectangular field for cattle having an area of 2,700 square meters is to be enclosed by a fence with an additional piece of fencing dividing the field vertically down the middle to keep the male and female cattle separated. The cost of exterior fencing is $36 per meter, and the cost of interior fencing is $24 per meter. Find the dimensions of the field so the total cost of the fencing is the least. Dimensions of the field. Okay, well, we know the area is 2,700. Okay. So I'm going to start out, and I'm just going to draw this to kind of think about this some more. So we've got a rectangular field. I could call this my my y, and I could call this my x. Oh, and it's divided down the middle. So maybe instead of calling this whole side x, maybe I'll just call this x and this x. Well, and then these will all be y. So it's cut directly in half, and it says the area is 2,700. So we know the area is equal to base times height, or length times width of a rectangle. Okay, well, I know 2,700 is equal to 2x times y, and that's the way that I want to handle it. You know, you might choose something different, but that's the way that I'm going to deal with it. And it says the cost, so let's see, cost is equal to 36 per meter of exterior fencing. Well, how many meters of exterior fencing do we have? All 4 x's are exterior and 2 y's. So I'd say 4x plus 2y. And then I'm beginning to think that maybe using double x's here wasn't really worthwhile, but it doesn't matter. I'm going to be able to answer my question no matter how I chose this, because it's eventually I'll find the dimensions, and so the dimensions I know that I'm just going to have to use 2 x's. Whatever I hit for x, I'm going to have to use double it. So 36 for exterior, 24 for interior. Well, that's 24y. Find the dimensions of the field so the total cost of the fencing is the least. Okay, well, remember that when we do optimization, our goal here is to have cost in terms of a single variable. That's all I care about. So I can come over here and go, okay, 2,700, pick a letter, solve for it. I'll solve for y, because I can. Actually, maybe instead I'll solve for x, because there's only one x in this equation. Maybe that'll make life a little bit simpler. I'm going to solve this for x. I'm going to change my mind. So I'll divide both sides by 2y here, and I'll get that x is equal to 2,700 over 2y. So that is, let's see, 27 cut in half is 13.5. So that's 1350 over y. And that's one of these lengths x. That's how I'm choosing to do this. It's the algebra that I'm going to do. So then I can say over here, 36 times, let's see, 4 times 1350 over y plus 2y plus 24y. Okay. This is just really nice numbers so far. 36 times 4 times 1350. And let me do that in my head really quick. Let's see. 34 times 1350. In my head, I got 194,400. While I'm at it, I may as well just double check. Yeah, okay. So, 194,400. Okay, so C is equal to 194,400 over Y plus 72y plus 24y. 72 plus 24 is 96. So c is equal to 194, 400 over y plus 96y. All right. So now when I take this derivative and set it equal to 0, that's really where we're going. So c prime is, remember, this is really times y to the negative 1. That's what over y means. So I can really say this is negative 194, 400 times y to the negative 2. Then we'll take the derivative of that and get plus 96. And then we'll set it equal to 0 and solve. Pay no attention to that pause and weird sound. Everything's fine. Everything's this. Okay, cool. All right, all right. There it is. Hey, I had paper the whole time. I'm professional. All right. So I'm trying to set this equal to 0. Well, I'll subtract the 96 from both sides. Get negative 194, 400. Y to the negative 2 is equal to negative 96. I'll divide both sides by the big number. You know what? I'm not going to find out what that is right now. And remember, this is 1 over y squared is equal to this. Okay, fine. Okay. You wanna know what it is? There. Is that? Ooh. I mean, sorry. It's 1 over 2025. Okay. All right. So there's two things we could do here. We could cross multiply. Another thing that you can do is you can take the reciprocal of both sides. That's a really dangerous mechanic because sometimes people don't really think about to what level that happens. So like just for example, really quick, if we had 3x is equal to 5 over y, I could take the reciprocal of both sides and get 1 over 3x is equal to y over 5. And this works because if we think about a cross-multiplying setup, we could say 3x times y is equal to 5, and then divide both sides by 3x, and divide both sides by 5. So the 3x's cancel, the 5's cancel, and we're left with the reciprocal. The issue is if I had x plus 3 is equal to 5 over y, if I were to try to take the reciprocal of this, I need to be very careful. So like multiplying both sides by y here, we'd get y times x plus 3 is equal to 5. So then I could divide both sides by 5 and still wind up with the y over 5. But when I divide both sides by the x plus 3, I get y over 5 is equal to 1 over x plus 3. So taking the reciprocal here, the error that people make is they go 1 over x plus 1 over 3. And that's not this flipped. That's each of them flipped individually. So I think that's one reason why people don't take the reciprocal of most sides, of both sides more often. So I'll flip it, I get y squared is equal to 2025. That feels like it's going to be a perfect square root. I can't be bothered right now. Hey, cool, all right. So y is equal to plus or minus 45 after we took the square root of it. But if we consider the implicit domain here, how in the world is a cow going to live inside of a fence that is negative 45 feet long? So according to my work here, y is 45. So now I just have to find out what x is. Well, I know that 2700 is equal to 2x times y, which is 45. So I'll divide both sides by 45. And I'll get 2700 divided by 45. I got 60, so x is equal to 60. All right, so x is 60, y is 45. So, oh wait, I'm sorry. I didn't get x is 60, I got 2x is 60. That means each of these little pieces here is 30, but I don't care about that. I care about the dimensions of the field. I care that the whole thing is 60. and that's 45. So a 45 by 60 field yay. All right. Oh, bad. Bad for two reasons. One, I didn't put meters. And two, I really need to just double check and make sure that this is a maximum, not a minimum. So if I go back here and I plug in if I plug 45 in, oh, right, sorry. All right, hey. It's not Friday. All right. So we got 45 for y. Remember, we can do the second derivative test to see if it's concave up or concave down. That's the easiest way to do this check really quickly. So c double prime, I'm going to get positive huge times y to the negative 3 plus 0, right? That's gone. So because of that, if I were to plug in positive 45, a huge number, huge positive number, times 45 to the negative 3 is equal to that huge number over 45 to the 3 equals a positive number, which means it's concave up! It's cup, wee! That means it's like this. That means cost when it's 45. That means this C is a minimum. Hey, that's exactly what I want. So this will give me the minimum cost. Okay, let's go to the next one. Very real world problem right here. Which point of the graph of y equals 4 minus x squared, points, is R closest to the point 0, 2? And so let's think about what this looks like. 4 minus x squared. That is a parabola. Y-intercept of 4, x-intercept of 2, if we think about that, plugging in 0. So yes, I'm going to do this without my calculator. So whoop, there it is. And whoop, there it is. All right. Which point on the graph closest to the point 0, 2? 0, 2. Okay. Oh, I've been reading this wrong. Sorry. Which ones are closet to the point 0, 2? Closest. All right. This indicates distance. And we remember that the distance is essentially the Pythagorean theorem solved for the hypotenuse. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. All right, so distance. We want the smallest distance, which means I'm eventually going to take the derivative of this. I don't want to take the derivative with all these letters. So let's see if we can figure this out. Well, we're taking the distance between some point on here, some xy point, and the point 0, 2. So to start out, I can just go in and say, okay, well, I'm going to pick maybe 2s or 1s. I'm going to have that be 0, 2. I am choosing to do that's a 0. I'm going to have it be the 1s. So 0, 2. Now I just got to plug in my x and y coordinate. Well, the x coordinate of any point on here we'd say is literally just the x coordinate. Here is the trick, more or less, for this problem. I could say the y coordinate, but there's a better way. Because I have two variables right now, I'd have to do implicit differentiation. Ain't nobody got time for that. So instead of doing that, I could say f of x minus 2 squared, which is still a little iffy. We're going to have to do some element of chain rule kind of oddly with that. Instead, what if we said distance is equal to the square root of x minus 0 squared plus, what is f of x? 4 minus x squared minus 2 squared. All right. This will be the distance between any point on here, any xy point, and the point 0, 2. And so now I just have to differentiate this. Blah. How about before we differentiate, we clean it up a little bit, see if it maybe will look at all nicer. So x minus 0 squared, well, I mean, that already is just x squared. And I could rewrite this second one, combine the 4 and the negative 2, and just say 2 minus x squared squared. So I'm going to FOIL it out. I don't know if this is going to wind up saving me time or making it easier on myself, but part of me thinks it's just worth doing this right now so I can have less parentheses to worry about. Oh, that was an x to the 4th. Sorry. Okay, I was talking. Let me double check. So that means do this twice. So it's 2 2's is 4. Then the 2 times negative x squared is negative 2x squared. That happens twice, so that's why it's negative 4x squared. And the negative x squared is positive x to the 4th. Okay. So I can write this as x to the 4th minus 3x squared plus 4. I am much happier with this than I was with this. When I take its derivative now, d prime, remember that's 1 over 2 square root, right? Derivative of the square root. Because, if we were thinking about the square root of a and we were taking the derivative of that, it's the same as a to the 1/2. Let me just leave it as x, fine. So then we bring the 1/2 out front, times x to the negative 1/2. And the shortcut, now the cleaning of that up would be 1 over 2 x to the 1/2. Clean it up even more, 1 over 2 root x. So that's all I'm doing here. I've done that so many times, I'm used to how that's going to look. But it's not x this time, it's bleh. So make sure we put the whole bleh in there. And then I'm going to be multiplying this by the derivative of the inside. I'm just going to put that on top, because multiplying it over here is the same as having it on top. So I get, I get 4x cubed. That's how I save myself writing. Instead of like going, oh, I need to cross that out, I'll just turn that one into a 4. So 4x cubed minus 6x, and that's gone. Okay. Nice, calm looking derivative there. Yum. Okay. So remember, as we're doing this, that there are 2 things that I need to check for. I've really only been saying over and over again that we need to check to see when the derivative is 0, but that's only partly true. We also need to see when is the derivative undefined. And maybe even before I do that, I should think about my original distance function and go, are there any issues here? I'm allowed to take the square root of 0, but I'm not allowed to take the square root of negative numbers. And so I want to make sure this never actually equals negative numbers. So at the same time, maybe I just want to solve and then go back and check and see if my solving is an issue. So like, basically, am I going to go hunt for a problem and then I can look out for it later? Or am I going to go and get a bunch of answers and then decide, then figure out if any of them are a problem? I think I'd rather do the second approach. So instead of going and making more work for myself, I'll solve this and then go back and see if anything's an issue. So we want to know if it's undefined or 0. As you go to 4x cubed minus 6x over, well, you know what? If we do the 0 part, then we can just ignore the denominator as we've done before. So this is pretty simple. We can divide both sides by 2 and get 0 is equal to 2x cubed minus 3x. Don't divide both sides by x. When you do that, you lose an answer. Instead of dividing both sides by x, factor that x out. So now we have 2x squared minus 3. X equals 0. You would have lost x equals 0 if you divide both sides by x. Both. I mean, that's a weird way to say that. On this one, 2x squared minus 3 is equal to 0. I can add the 3 to both sides, get 2x squared is equal to 3. So x is equal to plus or minus the square root of 3/2. So I'm going to need to go and check out of these three, what's the closest to 0, 2? And so, I mean, maybe the easiest way to do that is kind of go back in here and just check and see what happens. If I plug in 0, I get d is equal to the square root of 4, because 0 just cancels the x stuff out. So then that tells me, okay, so d is equal to 2. When we try the 3/2, the positive or negative won't matter because they're either getting squared or to the 4th power, so the negative is going to disappear. So 3/2 to the 4th minus 3/3 squared, oh sorry, square root, plus 4. So let's see, I got square root of 3 over 2. Oh, careful, Canfield. I'm going to do this in 2 steps. I don't trust myself. All right. So I'm going to say we have the square root of 1.5 squared. Nope, sorry, to the 4th. Minus 3 times the square root of 1.5 squared plus 4. Hey! This is the square root of 1.75 away, which last time I checked, the square root of 1.75 is less than 2, and so that means that plus or minus, oh, idiot, me, not you. These will be the x values. So I need to go back and I need to make sure I'm answering the question. It says which points on the graph of that. It doesn't say find some numbers. It says which points on the graph. So now that I've found those x values, I need to go in and say, okay, that's my x value. What's my y value? 4 minus square root of 3 halves squared. So 4 minus 3 halves. Well, that's 8 halves, so 5 halves. Okay. So my points are going to be, not positive or negative won't matter because the negatives will cancel. So it's going to be plus or minus square root of 3 halves, comma, 5 halves. You could write this as 2 separate points, or leave it as that 1 point, or leave it as the 2 points kind of combined. All right. And again, we could do the second derivative test. For some reason, I don't want to do that. Oh, this is so messy. So just kind of testing the values was fine for me on that one. All right, we've got 2 more egg samples. Let's see. A manufacturer wants to design a square-based rectangular prism box with a lid that has the largest possible volume. The box must have a surface area of 108 square inches. Find the dimensions of the box that maximizes the volume. So we want maximum this, max volume. And sa is equal to 2 bar plus 4 sa. Yeah, what? I mean, like JK, I know what it means, but okay, let's talk about it. I drew a box. Yay. Okay. The box must have a surface area of 108 square inches. So let's talk about that surface area. Okay, so if we called this length, we called this width, and we called this height. Well, rectangular prisms have 6 faces, right? 1, 2, 3, 4, 5, 6. So it's got these two, it's got these two, and it's got these two. So I'm going to want to add up all those areas for surface area. So I'm going to ignore this and just pretend I don't understand that and say, okay, well, my surface area is going to be the area of my front face, right? So I could just say is LH. How many of those do I have? I've got the front one, I've got the back one. So I could say 2LH. Now let's look over here. What's this one? Width, height. So I could say width, height. And there's 2 of those. So that accounts for 4 of my 6 faces. And then the bottom and top face is going to be length times width. So 2 times length times width. But. Manufacturer wants to design a square-based rectangular prism. L and W are the same. So this formula over here, I could say V is equal to LLH. Laughing like hoo-ah. Over here, I could say A is equal to 2LH plus 2LH plus 2LL. And these are very silly ways for me to be writing this, right? I should be saying volume is equal to L squared H. This area, wait, LH, this is 4LH plus 2L squared. All right. Now we're getting somewhere. The box must have a surface area of 108. This is 108. Has to be. So we want to find the dimensions of the box that maximize the volume. All right. I want to eliminate one of these 2 variables. I'm looking at H. I think it's going to be easier to solve for H. You do you. I'm going to solve for H. So I'm going to subtract the 2L squared from both sides and get 4LH is equal to 108 minus 2L squared. Then I'll divide both sides by 4L and get H is equal to 108 minus 2L squared over 4L. Sorry, 4L. And then they're all divisible by 2, and the more cleaning up we can do on questions like this, the happier we'll be. And I even question if there might be something better we can do, but let's plug it into the other one and see what happens. So if I go and I plug it in over here, I'll get the volume of, let's see, it's equal to L squared. And instead of writing H, I'm going to write 54 minus L cubed over 2L. Oh, hey, this is L squared times blah, divided by 2L. So I can cancel the L squared and one of the L's. So I could rewrite this as the volume is equal to 54L minus L to the 4th all over, whoa. I think I made a typo. Yeah, that was only L squared to begin with. So that's gonna be L to the 3rd now, all over 2. Okay, let me just double check. I just caught an error, so I wanna kind of go back. So that was an L squared, still was an L squared. So it was L squared times all of this. So 54L minus L squared over 2L, 54 minus L squared over 2L. And then the squared and one of the L's cancel each other. Okay. Sorry about that. That was an announcement. So all day it's been like snowing, and we've all been kind of waiting for snow. And I was like, cool, it's gonna be. Oh, it's just Reislers. Well, the wrestlers need to go to somewhere or other. Anyway, cool. And then I just distributed the L to the top. I feel like a lot of my students don't like looking at it like this. So another way we could rewrite that is we could say that this is 54L over 2 minus L cubed over 2. But again, a lot of people are uncomfortable with the idea of putting something over something like that. So you could even say this is 54 over 2L minus 1/2 L cubed. It looks uglier. I think this is a more elegant way to write it, but this is so much simpler to understand. This is 27L minus 1/2 L cubed. And when we take that derivative, it's a much simpler derivative to take. I want to pause really quick, and I just want to remind you like what the heck we're doing. So volume of this prism, of this box, is 27 times the length minus 1/2 of the length cubed. This is the volume. And what all this is it's a distillation of what's going on here. It's taking all the information about this box and it's saying, okay, can we reduce the box to one of its components and say, like, just based on one of its components, all this is true. So like we knew that the all right, start back. Okay, so we reduced all these components to the volume. So I can say, okay, volume is this equation. If I know the length, I know the volume, which is really cool. And we want to say, okay, I could try all sorts of different lengths. One of them, out of the bajillions of numbers I could try, from like 0 to infinity, theoretically, one of those is going to give me the most volume, right? So, and this is a very realistic problem. If we think about it like, okay, I only have so much material to work with. The more material I use, which is kind of how we can think about surface area here, the more material we use to make a box, the more expensive it is to make. And so what we do is we say, okay, how can I stretch this material out in such a way that I'm using the same amount of material, but I'm getting more volume out of it? And this is what companies do. I don't know if you remember, they've redesigned bottles a few times. So the little water bottles that they sell, because they're selling billions and billions of them every year. And so they find ways to eke out just a little bit more volume for the same amount of material. Or they'll say, ooh, let's keep the volume the same and reduce the amount of material. And so this is a very practical application of the calculus that we do. And so depending on what L is, as L changes, the volume changes. And so instead of having to just try all the different things, we can just take the derivative and say, okay, as the volume changes, this also changes. And we get the derivative. And we say, okay, the change in my volume is equal to this. My volume changes according to that derivative. So if I know what my length is, I know the change in my volume. And so what we do is we say, well, as I try different lengths, one of those is going to make the volume not change anymore. So like, oh, I'm putting it in, oh, volume's going up, volume's going up, volume's going up, volume's going up. We hit the perfect number and it makes volume stop going up. And then the more we put in, the more it's going to go down. And if you can look here, 27 3/2 L squared, we're really trying to find, okay, when do those basically cancel each other out? And that's going to be our optimal volume. So, sorry, I wanted to get less mechanical for a couple seconds because I can just burn through these problems all day and not really be helpful. Sorry, I already started doing it. So I'm going to add the 3/2 L squared to both sides. And then I'm going to multiply by the reciprocal of that fraction to cancel it. If you didn't know we could do that, that's the same thing as dividing by 3/2. So L squared is equal to 27. Well, let's see, 27 and 3. We're going to have a 3. Wait. 27 divided by 3 is not 3. 27 divided by 3 is 9. So we have a 9 left. So 9 times 2. 9 times 2 is 18. All right. And then we'll take the square root. And we get L is equal to plus or minus the square root of 18. Last time I checked, a length of negative square root of 18 is probably not going to produce a very large volume because negative lengths don't exist. All right, So I am going to clean it up. It's a 9 times 2 inside there. So L is equal to 3 root 2. Cool. So that's our length. So I'm going to go back to the question now. I've gotten to an answer. Find the dimensions of the box. Okay. Well, I need to go back and remember what I remember about the box, or what we know about the box. The volume is that. Our area is 108. Okay. And we know 4LH plus, we know that is 108. So I'm going to go in and say, okay, because I need to know, I know that this is 3 root 2. I know that this is also 3 root 2. But now I need to find, what is my Hiegit? Hiegit, or Hiegit. Quick sidebar. No. Or, it's not height. It's not height. It's height. If that's annoying that I'm emphasizing that, it's Mrs. Canfield's fault. No, I used to not know. Is it width? Well, I know it's length, width, and height. And I think I said height all the time. And one day she's like, I don't get why people say height. It ends with a T. And I was like, oh shoot, she's right. All right, anyway. So we know, let's see, 4LH plus 2L squared is equal to 108. And so I can go in and solve that now. I can say, okay, well, that's 3 root 2. So 4 times 3 root 2 times our height plus 2 times 3 root 2 squared is equal to 108. So I've actually kind of hurt myself here a little bit if I forget that 3 root 2 is the square root of 18, because this would be easier to do if I had left it at square root of 18. So this kind of goes along with that thing I've talked about in class sometimes of like, oh, I've shown this extra work. Look at all this extra stuff I know. And it didn't wind up helping me. It wound up hurting me. So I could say 4 root 18, or I could say 12 root 2 times h plus 2 times 18, which is 36, is equal to 108. Subtract the 36 from both sides. 4 root 18 times h is equal to 72. Divide. I'm going to divide both sides by 4. Divide both sides by 4, and then also the square root of 18. So our height is equal to, let's see, 72 over 4. 20 is too big. 15 times 4 is 60. So I think is it 18? I think it's 18. So 18 over root 18. I'm going to just double check really quick, because I'd really hate to be wrong on the internet. So this and this, there's a couple ways to check. I like to do this one where you square it, and then, oh yeah, right, so, because that would be, this, it would just, so you could do square root of 18, square root of 18, and get 18 root 18 over 18 and get the square root of 18. So I square it and go, okay, whatever I get here, I just write the square root of that, and that's my answer, and sure enough. So, okay, this is very strange. Length is equal to 3 root 2. Width is equal to 3 root 2. Height is equal to the square root of 18. 3 root 2. What shape is that? It's a cube. Whoa. Did you know that if you fix the surface area, the maximum volume will happen when it's a cube? If you didn't, you do now. This always happens. It does not matter the dimensions. And you can kind of extend this idea. You know, no. I'm not going to talk more about that. I'm not going to tell you secrets that you shouldn't know yet. All right. I'm going to make fun of Delawareans now. 2 posts, or maybe that's Philly, I don't know. 2 posts, one which is 12 feet high and the other is 28 feet high, are 30 feet apart. Okay. One which is 12 feet high, the other which is 28 feet high, are 30 feet apart. 30 feet apart. 30. All right. They are supported by 2 wires attached to a single stake in between the posts, running from ground level to the top of each post. So there's a stake in the ground. Maybe it's here. Yeah, it says where should the stake be placed. So it's not necessarily right in the middle. And we want to know, or like, so bing and bing, right? So here's a post supported. So, you know, it's like stuck in the ground with a wire going down to the ground, holding it up, like helping support it. For some reason, my brain keeps on going, they are supposed, but it says they are to be supported. It says, where should the stake be placed to use the minimum amount of wire? Woof. So, wire. So, we're getting really cheap here, okay? And this is legit things that people do. You know, we've got these 2, I'm just going to trace the scenario a couple of times. All right, so like we want to know, okay, if I put the stake right here, then use that much wire. If I put the stake way over here, and use that much wire. I don't know if you can tell, but it seems like this wire is probably less than this one. And so we want to try to find some place where the wire is going to be the least. And we could move this all over the place all day and keep on guessing. And eventually we'd probably get there. But instead of having to do that, we can create a set of equations, take the derivative, and have a much easier time. So first I'm going to focus on things that are not moving. Let's see, so I know that's 12. I know that this plus this is 30. So I'm going to say this is B, like for base, and then this is 30 minus B. That's how I'm going to refer to that. It's going to say, the less variables I can use, the better. So then this guy right here and this guy right here, let's see. We have to assume that they're going straight up and down. Otherwise we can't do it. So I can actually find the third side of both of these triangles. I can say, okay, well, this one is 12 squared plus B squared is equal to my first wire squared, right? So I could say this is the square root of 144 plus B squared. And then do the same idea here. I could say that this is, we'll call that wire 1. So for wire 2, I can say, well, if I take my 30 minus B and square that, and I add that to 28 squared, I'll get my wire 2 squared. So then wire 2 is going to be a square root of that. So I can say, oh, wait, hold on. Maybe I should clean this up first. That might make life a little bit easier. Kind of like we did earlier in the video. So that's 900 minus 60B plus B squared plus, okay. If I want to square 28, 28 times 28 is almost 30 times 30. It's almost 900. So if I did 29 times 30, I'd get 900 minus 29. So that's 871. And whatever, just do the 784. Okay. Boom. I did it in my head. So, let's see. So b squared minus 60b, 784 plus 900, 1684. Why am I using my calculator? Okay. So I take the square root of that. So, all right. So square root of b squared minus 60b plus 1684. Cool. All right. So, the amount of wire. So wire is equal to square root of 144 plus b squared plus square root of b squared minus 60b plus 1684. That's our wire. That's how much wire we're using. So if I want to minimize the wire, take the derivative. That's it. And so to do that, so w prime is equal to 1 over 2, 144 plus b squared. Remember, it's a square root, just like we had before. And then take the derivative of the inside. That's going to be b squared, so times b squared. Oh, whoa, not b squared, sorry. Times 2b. Derivative of that's 2b. So same thing for this one. And then derivative of the inside of that is 2b minus 60. Okay. Now we're going to set this equal to 0 and solve. And I'm sure you're thinking, well, that's so simple. You're right, it is. It's going to be so simple. Try not to cry. So we set it equal to 0. You know what? We can cancel those 2's. And over here, we cannot cancel those 2's. Oh my gosh. That minus sign wrecks it. Can't do that. We could divide them all by 2, though. There. Okay. Now they're canceled. I'm going to subtract this one over there. So it's equal to 0. Subtract this one over there. So negative b minus 30. That's me subtracting it. Square root of b squared minus 60b plus 1684. 1684. Good year. That's when I was born. So old. If you are actually watching this video, you should make a comment about how I was born in 1684 in class. And